Question 5. This question is about pair of 3 elements in a compound. So already, pair of 3 elements in a compound, I already know there's going to be at least one question on equations, because that's the whole topic of pair of 3 elements in a compound. It's like 2 pages, and it's full of equations and just key details you just need to memorize. So this question about pair of 3 elements in a compound, which is not a correct statement about magnesium hydroxide. So which is a correct statement, which is not a correct statement. So which is false. Don't want to get confused. So which is false? It is used to neutralize stomach acid. That is true. That's definitely true. It has the empirical formula H2MgO2. Well, let's think about it. Magnesium hydroxide, MgOH squared. So yeah, you would get MgO2H2, which is the same as H2MgO2. So that is true as well. So therefore this one must be false. Forms a solution with pH equals 14 at 25 degrees Celsius. Yeah, most of these 1 markers where it's tick a box, you can just do it by trial and error. By understanding that's true, so that must be false, or vice versa. Given equation for reaction of aluminium oxide, Al2O3 plus H2SO4 to form Al2SO4 3 plus 3H2O. So already an equation, and there must be a 3 here. 3 sulfurs, 3 there. So Al2O3 plus 3H2SO4 to form Al2SO4 3 plus 3H2O. Identify a region or test that could be used to distinguish between aqueous solutions of sulfur dioxide and sulfur trioxide with the same concentration. Sulfur dioxide, SO2, sulfur trioxide, SO3. So a region or test to distinguish between aqueous solutions of it. 5.3, 4, 5, and 6. That's it. And question 5. Just see how many questions there are. So let's say universal indicator. There was a different one that we could have chosen, a metal like magnesium, calcium, or zinc, and SO2 would have a slower effervescence, SO3 would have a fast effervescence. But let's just use universal indicator. SO2 is going to have orange dash red, and sulfur trioxide is just going to be red and aqueous. Universal indicator, observation of sulfur dioxide solution, orange dash red, observation orange slash red, observation of sulfur trioxide solution, just going to be red. 5.4, the mass spectrum of the element phosphorus has its peak at m/z equals 124. Give the formula of species responsible for this peak. I've never seen this type of question before. This is an A-level paper. Two marks as well. A peak at m/z equals 124. So we know it's going to be phosphorus, so let's write P4, and it's going to be, it's going to be 31 P4 and a plus charge. 31 P4, actually let's do it again, 31 P4 plus So phosphorus oxide P4O10 plus 12NaOH to form 4Na3PO4 plus 6H2O. P4O10 plus 12NaOH, 4Na3PO4 plus 6H2O. 4 mark. Draw a displayed formula of the molecule formed when phosphorus oxide reacts with water. Well, phosphorus oxide P4O10 reacts with water. It's going to be P. It's definitely going to have a double bond with an oxygen. We're going to have an O and a H. We're also going to have another O and a H, and we're also going to have another O and a H. So P with a double bond O, OH, OH, OH. And then the final part of question 5. 6 marks. Table 4 shows the melting point of 3 substances. Explain why the melting points of these substances are different. You should refer to the structure of and bonding in each substance. 6 marks. Okay, so sodium chloride, chlorine, hydrogen chloride. Well, sodium chloride has the highest melting point. Why is that? Well, sodium chloride is giant ionic. It's got ionic lattice. Giant ionic. Chlorine, well, that's molecular. And so is hydrogen chloride. So stage 1 is going to be on the structure. So we know that sodium chloride has a giant ionic lattice. Chlorine is molecular, simple molecule, and hydrogen chloride is molecular, simple molecule. Stage 2, let's talk about the intermolecular forces. Stage 2, forces. Forces. So we know that because sodium chloride is giant ionic lattice, or giant ionic, and it's got ionic lattice, NaCl, or sodium chloride, has attraction between positive and negative ions. Chlorine has van der Waals forces, and hydrogen chloride has dipole forces. And now stage 3, what we actually wanted to do which is compare the melting points. So comparison of melting points. So okay, I don't know what just happened there. I think it just zoomed in by 10%, but it's fine. We know that there we go. We know that because sodium chloride has a giant ionic lattice, it's got ionic bonds, and ionic bonds are stronger than the intermolecular forces. Hence, sodium chloride has a significantly higher melting point than chlorine and hydrogen chloride. Chlorine is a bigger molecule than HCl, than hydrogen chloride. Hence, chlorine has more electrons than hydrogen chloride. Hence, stronger forces between molecules in chlorine than in hydrogen chloride. Stronger intermolecular forces. Yeah, and we also know that van der Waals is greater than dipole-dipole. It's hydrogen bonds, then van der Waals, then dipole-dipole, then all the melting point. And because chlorine has van der Waals and hydrogen chloride has dipole-dipole, chlorine is going to have a high melting point. So, stage 1 on the structure: sodium chloride, ionic lattice, or ionic lattice. Yeah, ionic lattice. Don't really need the word giant. Ionic lattice or giant ionic. So chlorine is molecular, simple molecule. Hydrogen chloride is molecular, simple molecule. Stage 2, the forces responsible for the melting points. While sodium chloride has got an ionic lattice, therefore it has attraction between positive and negative ions. So attraction between Na plus and attraction between Cl minus ions. Chlorine has van der Waals forces, and hydrogen chloride has dipole-dipole forces. And then stage 3, a comparison of melting points. Well, we know sodium chloride has attraction between positive and negative ions. Ionic bonds, which therefore is an ionic bond, ionic lattice. Ionic bonds are stronger than intermolecular forces generally. Hence, sodium chloride has a significantly higher melting point than chlorine and hydrogen chloride. And now comparing chlorine and hydrogen chloride, why does chlorine have a slightly higher melting point than hydrogen chloride? Well, chlorine is a bigger molecule. You know, HCl versus Cl2. So you've got 2 of this, but you only have 1 of this in this case, plus a hydrogen. And hydrogen is not a big molecule compared to Cl2. So hence, chlorine has more electrons, which is true, than hydrogen chloride. Hence, stronger forces between molecules in chlorine than in hydrogen chloride, are stronger intermolecular forces. Van der Waals forces are stronger than dipole-dipole forces. And then that is the end of question 5.